First, this was cracked by some Russian hackers in 2003 that found out, oh, the Nokia mobile phones actually ship with debug symbols. What we wrote is a program that can actually decode this GSM message according to the specification, which are really horrible. And I'd guide you through some example traces that we did. And this is an example trace of, I think it's initiating a phone call. And yeah, let's see how this goes. Paging request first is done by the base station, and asked for the mobile phone. Hey, mobile phone, where are you? Are you there? And yeah, let's go on to the next one. And at some point it tells the mobile phone, there's something happening for you. Please go onto this dedicated channels, SDC/8, whatever, and just get onto this channel and tell me when you're there. And let's go to the next one. And then it says, mobile phone, please tell me what your identity is. And now you have to realize the GSM specification says that your IMSI should never ever be sent over the mobile network, okay? And this is pretty much the first trace that we did. So let's go to the next slide. Oh, no. Oh, who thought that? Who thought that? Like the first trace we did and we see already the IMSI? Well, fine enough. Okay, so this gave us hope. Basically, it's the first trace that we did. We opened, I mean, no one ever has done this before. No one ever verified what these companies are doing, what the mobile radio are doing. And we opened that door that much, right? And what comes out is already shit. That's great. That gave us a lot of hope. Okay, so we see the IMSI. The mobile phone says, this is my IMSI. What do you have for me? And the BTS says, yeah, I have something. And actually, I support the encryption A5/1, which is indicated by the bit 0, and I support A5/2, which is indicated by bit 1. You know, no one knows why. And yeah, that's it. Then the mobile phone responds with, that's great, this is my random number. No, sorry, this is a base station actually. Sends a random number to the mobile phone, because the mobile phone has to authenticate itself, tell them, okay, that's really me, and you can charge me on my calling plan. And the mobile phone responds with an address. And at that point, the mobile phone is fully authenticated and is allowed to do a phone call or receive a phone call, or is allowed to send an SMS. And the ciphering is initiated. Cipher chosen by the mobile phone is A5/1, starts ciphering. From that point on, everything is encrypted. Now, the good thing about the Nokia Trace Mobile, in difference to the USRP, is that the Trace Mobile gives us everything after decryption, okay? So the USRP, when we tune in to a base station, we only receive the encrypted messages. Now what the Nokia Trace Mobile gives us is after decryption. So we can actually see what are the actual packets compared to what do we receive on the USRP and what do we actually receive on the mobile phone. And we can compare these packets. And that helped us a lot performing our A5 attack, which David will explain later. Cool. And of course, we already sent the IMSI, which is the International Mobile Subscription Identification. It would be a shame if we're not sending the IMEI, the International Mobile Equipment Identification. Okay. So actually, everyone also knows what kind of handset you're using, which is quite good. And there's another thing. Did anyone ever lost their mobile and you try to ring the mobile operator and you tell them, yeah, I lost your mobile, can you tell me where they are? And they tell you, oh no, you can't, you have to buy a new one. That's bullshit. I mean, your mobile every time transmits where it is. It transmits its identification and it transmits where it is. The mobile operator knows very precisely 200 meters where your mobile phone is located. Okay? So this is a big lie from mobile operator that they don't know where you are. 200 meter precise. And if you're a little bit tricky, you can get it to a couple of meters precise. Okay, cool. Let's get on. Okay, security in GSM. This is GSM network. We have seen this before. And this is where the security happens. Let's go to the next slide. In GSM, the only part that is encrypted is the air part. As soon as it hits the base station, from that point on, everything is clear text. So anyone with access to the base station can plug into the switch, and there's a monitor port in the switch where you plug in your Windows laptop, and you have a special software, and you can listen to any traffic, okay? And this base station usually is protected by padlock or, you know, something like that. It's not protected. They're just anywhere in the forest. You've seen them. They're in the forest. Okay, this is encryption. And this encryption was already broken in 98. Ah, okay. This encryption was broken in 98, but how was it broken? The encryption was broken by people from the university. And from people from the university, they say it's broken if you can crack it in 1,000 or 2,000 years, and it's declared broken. But practically, you can still not read it. So actually what we came up with is the first ever attack that only requires the first 3 or 4 GSM frames to crack a GSM conversation. All other attacks available require at least 2.5 minutes of conversation. We only require a couple of milliseconds, really. But David will tell you more about that later. All right, let's go on. Yeah, GSM security, A5, A2, it's a weaker algorithm. Some historical background. Initially, the countries were undecided if they should use strong encryption or weak encryption. France didn't want to have any encryption. Germany wanted to have strong encryption because they were bordering to the Soviet Union. And they decided, yeah, so we give some countries A5/1, the strong encryption. And for all people who doesn't want it, we give them a weaker encryption. It's A5/2 or A5/nothing. Okay, mobile operators always know your pre-shared secret. There's not a session key negotiated, it's always a pre-shared secret, which is in clear text stored in the mobile operator database, okay? It's clear text stored. Anyone with access to the base station can read your traffic. Anyone. And this is something that people don't realize. Past conversation can be decoded. If you throw away your SIM card and someone before recorded this encrypted traffic and he gets access to your SIM card, he can decode all the traffic without a password, without a PIN, without anything, okay? So never again throw away your SIM card, burn it or eat it. Never throw it away. People can listen to what you said in the past. Let's go on. Okay, this is the last slide that I have before I hand over to David. And I want to talk a little bit about what we're trying to achieve with the USRP and with the GSM scanner project. We want to go into sending. Right now we can only receive. If we can send, hell yeah, we can have a baby cell. We can create our own pirate GSM cell. We can offer people free GSM calls in that cell. Well, on 35 kilometers, quite a big cell. Covers billion. This would be quite nice to have free calls there. We can do some, security stuff, man-in-the-middle attacks, and actually we can scan for phone numbers, like which phone numbers are in my area. We can brute force, or we can play with accessing the database of the mobile operator. We can have free calls, or we can track people where they are. Oh, actually, sorry, tracking people we can already do. We can already find out with just one USRP where you're located to roughly 200 meter precise. So with one USRP, we can already track people and see where they move to. And yeah, that's me. Thanks a lot. Later on, we have some questions, and I hand over to David, who will tell you how we crack A5. And that'll be fun.
Thanks a lot, Steve. So, with the A5 cracking project, just to give you a brief intro here, when we were looking at starting this project, we were looking at only practical attacks we could actually implement and could actually crack conversations that weren't, multiple minutes long, and something where we could actually just drop it somewhere and then maybe record conversations, and within a reasonable amount of time actually be able to decode them and listen to what people are saying or sending SMSs and stuff. So originally, we only looked at ciphertext-only attacks, and a lot of these attacks seemed like way too complex and required a lot more time, for the over-the-air capture than we really wanted. And so we actually ended up finding out through Steve's research that there's tons of known plaintext. The first 4 packets are entirely known, and so that equates to 456 bits of entirely known plaintext. And so then after we found this out, we geared straight towards just known plaintext attacks on that single, 4 packets that are sent out at the beginning of the conversation. So we researched a few different attacks. If you guys are familiar with any of these GSM attacks, there's this Anderson, Rowe, and Keller attack where I'll cover it a little bit more, but it's essentially taking the the output that you know straight out of A51, and then using the data that you know to basically find information about the registers inside A51. And I'll get into that a little bit more. We also looked at doing pre-computation because we're essentially brute forcing around 64 bits, which is a lot of bits. And if we could possibly build a rainbow table for this, then it would reduce our real time, of the actual attack. And so we borrowed some things from other people and kind of melded it together to make it fairly practical for what we're looking at. And both of these attacks, we are actually accelerating with FPGAs. So if you happen to have an FPGA board, then you'll be able to speed it up and make it actually happen within, a matter of minutes instead of days or years or whatever. So looking at A51 internally, I'm just going to describe how it works here. You have these 3 different shift registers here, and and essentially how it works is whenever this whole thing is clocked, it looks at these clocking bits, 10, 10, and 8, and then it finds out the majority of like which ones agree with the majority. So like if all of these are 0, then all of them are clocked. If just these 2 are 0, then these 2 are clocked. If just these 2 are 1, then those 2 are clocked. And then this one is not, because it's only the majority ones that are clocked. And when they're actually clocked, they end up taking these different tap points in here. So 18, 17, 16, and 13. They're all XORed together, and then they shift in on this side. And then this bit comes out and gets XORed over here. And this is the actual output of A51 that gets XORed with your actual plain text. And that's how everything gets enciphered. So to actually mix in the key into the shift register, you take your 64-bit key that actually comes from the SIM card, and then you actually feed it in over here. And so on the first clock cycle, we'll take the first bit of the key and then XOR it in with those bits, which should all be 0 initially. And they get fed in through here. 0 bit gets fed in through here, and so on. And then you go bit by bit and start clocking in all 64 bits of the key. Then you take this frame number, which is unique to the frame, and it's 22 bits. And then that is actually kind of like an initialization vector, and it's sent in plain text in the frame. And that actually gets mixed in the same way that the key does. Then it actually runs, after it mixes in the 22 bits, it actually runs it for 100 clock cycles to just mix everything around inside the registers. And then after the 100 cycles, it actually starts clocking it forward and generating essentially like pseudorandom output out the other side based on the key. And that gets XORed with the plain text and sent out. So this Anderson row attack basically works on this premise that the bits that are sent out over here, if you know the actual output of A51, you can guess these 2 registers, and essentially this third register, or one of the registers, will kind of be like parity, where like if you know this bit, and that bit, then you can calculate this bit down here because it's just an XOR operation. So that can be reversed back. The only tricky part with this is that with the majority clocking, it makes it somewhat of a one-way function. So when you're actually like reverse clocking this, you have to kind of guess what the clocking bits are here, and I'll go over that a little bit. So yeah, the output bits are related to the register bits. And essentially, you're basically brute forcing these clock bits down here, and trying to find out the right clock bits that will actually generate that output. And there's a couple things you can rule out, use to rule out different possible bits inside the third register. And how this works is that, like for example, if this register down here isn't clocked, and you kind of hypothesize that this doesn't match the majority here, then this bit should match up with the known plain text over here. And so if this bit changes and these match up, then it turns out that it actually doesn't clock it. And I'll put code up later so you can actually take a look at it and see how it works. But